going to talk a little bit about circuit basics and Ohm's Law. So one of the things that we've kind of discussed before is what is known as electric potential. So in order for a charge to be moved, when we did electrostatics, one of the things that we learned, in order for a charge to be moved, work has to be done. And that work is energy, and energy is work. Work is energy, and energy is work. And since that's the case, we're talking about electrical energy. And since we're talking about moving its position, we're going to say that that's electric potential energy. So work is the electric potential energy. Now, when work is causing a charge to move, or the amount of energy given to each charge, that is actually known as electric potential difference, or what you may commonly know as voltage. So electric potential difference is the amount of work or electric potential energy per the amount of charge. Now, there's several sources of that electric potential energy. One of those would be batteries, and an electric generator is another good example of an electrical source. And what it does is it acts as a pump. It basically provides the energy. It takes the chemical energy in the battery, and it's going to convert that chemical energy from a battery into electrical energy, and each charge gets a certain amount of that to make it move. Now, home outlets in America are 120 volts. If you go overseas, they're 110. But if you look at the big outlets behind the washer and dryer or behind the refrigerator, you're going to find that those are 240 volts here in America, and I believe they're 230 volts overseas and in other countries. And there's also a third prong, that's a grounding line. It allows charges to move to and from the ground. Now, basically, we've provided energy to the charges, and this is going to cause the charges to flow. So if there's not a difference in the amount of energy, those charges will not move from one location to another location. And so we have a flow of charge. So only if there's a difference. Now, this is the reason why birds can actually sit on a high voltage power line, because if there's no electric difference, then they would not be electrocuted. No current would flow. It's the current that actually is damaging. It's not the voltage. It's the current that actually is the problem. So if you stick your finger in an outlet, it's a very dangerous thing, not because of the voltage, but because the difference in the energy causes that current to flow. So current is the amount of charges that pass through a point in a certain amount of time. Current is represented by the symbol I, and it's measured in A for amperes. I is for current. In an equation, it's the symbol in the equation, and the unit is A for amperes. Now, Q is for charge, and it's measured in C for coulombs. T is for time, and it's going to be measured in S for seconds. Now, resistance also occurs. You may have heard of something called a resistor. A resistor gives resistance, and basically it's the opposition to the flow. So one of the things that can happen is if you get too much current passing through, the wires can get heated. It's kind of like if you rub your hands really fast together, you get a lot of heat. So if the current or the charges are moving way too quick, you get a lot of heat created. So we put resistors in a lot of our electrical devices to kind of slow that down. At the same time, if you put too much resistance, you get a backup, kind of like a clogged pipe, and that can also create a lot of heat and frustration as well. So it's not a really good situation there. So too much resistance can be a very bad thing. Too little resistance can be a bad thing. You need just right. And it kind of sounds like Goldilocks and the Three Little Bears. So This is what some resistors look like. You can see a variety here. A lot of the ones that we have these bands on them, and those bands, the colors of the bands actually dictate the actual amount of resistance, and they can actually be read. There are apps for reading resistors. There's also a color code chart that you can find online for reading resistors and figuring out how much resistance they have. Now, Ohm's Law, we have a law. It's called Ohm's Law. And so we need to learn a little bit about Ohm's Law. And a lot of times people will say it's V equals IR, but actually it's the current is proportional to the potential difference. And that's only if it's at constant temperature. So if the temperature is changing, this law actually doesn't apply. So your standard light bulb, technically this doesn't apply. But like many things in physics, we assume an ideal world where things like this are not actually happening. And so V equals IR is assuming that the resistance is staying constant. But a regular filament lamp light bulb or even your LEDs can get warm, and so they don't truly obey this law, but it is the best prediction of what these values would be. So in the equation, we have I for current, and that's measured in A for amperes. We have V for potential difference, which you may know as voltage, and it's measured in V for volts. And then we have R for resistance, and it's measured in omega, which is that horseshoe looking symbol, which is ohms. So resistance, which is the R in the equation, is measured in ohms, which is the symbol omega. Okay. And of course, if our voltage is constant or potential difference is a constant value, then as the current increases, the resistance decreases, or as the resistance increases, the current decreases. Now, if the resistance were to be constant, if we increase the potential difference, then the current would proportionately increase as well. What's really important here is that you recognize the symbols and the units, and you're able to use V equals IR. So in circuits, we actually don't draw our actual light bulbs full out. We use symbols really to represent the parts in a circuit. So here you can see we have a light bulb, and you can see it looks like a zigzag with a circle around it. We also have a battery, and you'll see that it looks like a long line and a short line. The long line represents the positive terminal of the battery, and the short line looks like the negative terminal of the battery. And just the black little lines that you see, those are wires, and they're representing the wires in the circuit. So a wire in the circuit is just going to be a straight line. If it's a resistor in a circuit, it looks like a zigzag. A light bulb or filament lamp is going to look like a zigzag, but with a circle around it. If it's an outlet, a plug, it's going to be a long line and a short line and a circle, so it looks really a lot like what you'd be plugging into. A single battery is a long line and a short line, with the long line being the positive and the short line being the negative. And if you have multiple batteries, then you're going to see multiple long line, short line, long line, short line. So here, when we see multiple batteries, we actually have 3 batteries in this picture where we have multiple cells. There's 3 of them here because I have a long, short, long, short, long, short. And then we have a switch, and a switch kind of looks like a switch. So here you have an open switch, and this is what a closed switch would look like. And it's really important that you are able to kind of recognize these schematic diagrams, these circuit symbols that we would be using to represent the different parts in a circuit. Now, current is able to be measured. We use what is called an ammeter. Since current is measured in amperes, an ammeter is used to measure it, and it's represented by a circle with an A in the middle of it, and that measures current. To measure voltage, or what is also known as potential difference, you'll see a circle with a V in the middle of it for a voltmeter. And then if we wanted to measure resistance, we would use an ohm meter because resistance is measured in ohms. And so that would be the case for that. So these are different parts of the circuit symbols, the basics of the different elements that we would be talking about in our circuit unit.